So, good evening, everyone. So, let us start today's session. So, can you able to see my screen? Okay, thank you. Okay, so we'll continue threads and blocks. So, this is just a recap only. So, in this particular program, so what we are trying to do is how the threads are thread IDs are assigned. Okay, and how many threads we are using, so and how many threads have been created. Okay, so as usual, here in this program, simply we are calculating id. Okay, thread id. So thread idx dot x into block dimension dot y plus thread idx dot y. Okay, that is assigned to a matrix. Here we are having the n value 5 and m value 6. Okay, so the block is defined in 3 dimension. So that means number of threads n comma m comma 1. Okay, so here we are having matrix. Okay, so we have to allocate the memory space for the matrix, and because we are assigning the thread id, that is id of thread, to some matrix, so we need some uh, what I say is some dynamically memory locations, so for storing the ids in the gpu. Okay, that is allocated here. And the H matrix, which is there in the CPU. Okay, for that also we are allocating memory. So here we are calling both block and threads. Okay, so here threads are represented in three-dimensional way: dim3 n comma m comma 1. So that is named as block. So you can give it as a block. Actually, we are using only one block. So how many threads we are using is n comma m comma 1. Okay. So in a block contains 5 into 6. So 30 threads are there. Okay. So next, once all the values are have been calculated and stored in the array, so next we are copied back all the data to CPU. Then we are printing. Okay, less than m, less than m. So then we are multiplying IA with m plus jj. Okay, after that it will be stored. Okay, so you can execute this program. Sorry, I couldn't execute. So if you are having any problem with execution, let me know in the chat. Sorry. From where for unsigned? 1 second unsigned. So just execute the program and let me know the result, whether you are able to get it or not. So, okay. So, I got the result. Okay. So, how many threads are there here? We are having 5 into 6, that is 30. So, it will start from 0, 0 to 29. Okay. So, the second program, there is a slight changes in that particular program. Okay. So here in the previous one we have used x dimension and y. So here y dimension and x. Okay. So while executing this particular program also, all the remaining things are same. There is nothing changed in the there is no other things changed in that program. So only the dimension is changed. Okay. So you'll be getting the same. Okay, if you run the program, you will be getting the same result. Okay. So from this we can conclude that, so whether the one dimension, whether if you are using one dimension or two dimension, so other more than three dimension, so you can achieve that too in the one dimension too. Okay. See here, sorry. So same thing. Here, what happens is block adx dot uh, x into block dim dot x plus thread adx dot x. Okay, all the remaining things are same. So you try to execute this one too. Otherwise, you simply change all the dimension to xxx and execute the same program. So you see what will be the result. Someone execute and you can post the output. You change all to XXX. So what is the reason behind this particular thing is, if you have used, if you are using multidimensional data, anyhow it will be accessed and executed in the GPU in an dynamic memory. Okay, so all the calculations happens. So you couldn't do the multi-dimension storage there in the GPU. Okay, so you can do it in single dimension only. So uh, because we are allocating memory dynamically. Okay, so that is only the reason we couldn't allocate memory in other way. Okay, we couldn't allocate statically. If we can able to allocate in dynamic only. So anyone have you executed? No, then no problem. We'll move to the next one. So you can perform computation on multidimensional data using a one-dimensional block. Okay, so you can use one-dimensional block and you can execute. So here it is one more change is there. Have you understood the change? No, no, no. There is one more small change is there. You see that program. One more change you have to do. So initially, what we have done is before going for two-dimensional and three-dimensional. So if you are using um, okay, so in this program, I'll tell. So you are having the block n comma m. Okay, we are defining dim3 with block n comma m. So in the single dimension, so here there is no other dimension, so there is no need to give the dim3. Here dim3 is not here. Okay, so dim3 is not there. So directly the n comma m value is given in the kernel logic itself. Okay, so you have to remove that statement too. Okay, the previous two programs, so only the dimensions, this is the first one. This is the first one, only dimension is changed. All the remaining things are same. And the second one, y. So this one is alone changed. And the last one, the one dimension. So we are having only one dimension here. So there is no need of that dim3. Okay, so in dim3, it is specifically for two dimensions or about two dimensions. So, okay, so if it is having one dimension, there is no need of that particular statement. So you directly give the number of blocks and number of threads here. Okay, so if you change that one, you will get the result correctly. So next one is matrix multiplication. So you know what happens while calculating matrix multiplication. You are having two matrices. So rows of matrix A has to be multiplied with the matrix B, and you are adding. Okay. So here in this diagram it is mentioned. So this one is multiplied with this one and written here. This one is to be multiplied with the first column of B and has to be written here, and this multiplied and summed up and written here. Okay. So here uh, one block of threads compute. So there is two matrices are there, MD and PD. So in PD matrix, one block of threads compute matrix PD, and each thread computes one element of PD. So for each and every element in a matrix, okay, so this is a product matrix. This is a ND, and MD is multiplied and it will be stored in PD. And in PD matrix, each thread computes one element of PD. Okay, so here each thread, what it will do is it will load a new row of matrix MD. So actually, one row is handled by one thread. Here, one column is handled by one thread. Okay. So next, what it has to do is it has to multiply 3 into 2, 2 into 4, 5 into 2, and 4 into 6. After that, everything has to be added together. Then it will be stored here in the product matrix. Okay. So here one column, here it is row is handled by one thread and column is handled by one thread. So here what you have to do is the size of the matrix has to be limited by the number of threads allowed in the thread block. Okay, so you have to decide that. Okay, so here one more thing you can consider is, so you can give the tile width too. So tile width is nothing but so number of threads in a block. Tile width is nothing but number of threads in a block. Okay. So block size equal to tile size. That means how many tiles you needed. That will be equivalent to the number of blocks you are going to use. Okay. And tile width is the number of threads in that particular block. Okay. Okay. So this again the same one. Okay. You can see here. Here, there is one matrix is there. Okay. So here, tile width is considered as 2. That means this P00, P10, P01, P11. So these 4 threads comes under block 00. And these 4 threads comes under block 10. And because of tile width 2, so each and every block, it is having 2 cross 2 threads. Okay. So it will be done with already we have seen. So here it is multiplied in this way. So here, how many number of rows and how many number of columns are needed. Based on that, you can decide the block according to the tile width. Okay, you know that how the matrix multiplication happens. That is simulated here. Okay, that's all. Nothing else. Okay, so the square matrix multiplication using C code. Okay, so here what you needed is, you needed, you have to declare matrix A, matrix B, and matrix C for your product of two matrices. So you have to, you know already how to write the code for sequential code for matrix multiplication. Here it is having three for loops. Okay, and it is having three for loops. Of course, the number of multiplications. So here the basic operation is the multiplication and addition. Okay, so both multiplication and additions require big OH of n cube. Okay, so n cube multiplications or n cube additions needed. So if your value total number of elements in n, you have to access n cube times. Okay, all the n elements. So it is very high. It's a exponential time complexity. And in your GPU computation, you don't have any for loop type computations. So how can we convert this C code into a GPU code? Okay, so you know that the same thing is simulated here, there, and there. And single value of Cij, only a single thread can be necessary to traverse the I through. Already I told that for traversing one matrix row, you need one thread, and one matrix column, you need one thread, because you are multiplying row to column, row of one matrix with row of another matrix. Okay. So the number of threads needed to compute the square matrix multiply is n square. For you are having, you need n square threads. Here we are having the C function and the CUDA kernel function. Okay, so already we have seen the C function in CUDA kernel function. So what you have to do is, you have to multiply row with column. Okay, you have to calculate the index for column. You have to calculate the index for row, the column in x direction and the row in y direction. After that, so you have to verify whether column is within the width or row is within the width. Then what you have to do is, you have to multiply row and column and add it together. Okay, so that is done with the help of this formula. Then you do this. Okay, so this is a GPU kernel. So if you are using tile width, okay, so instead of block dimension, what you have to do use, you have to use tile width. That's all. All the remaining things are same. Okay. So I have already executed the matrix multiplication program Nicola. I'll show, but I couldn't execute today. The complete program is available with the help of tile width. Okay, here also I have calculated the running time and all, and using the tile width we are calculating the column index and row index. After that I'm calculating everything. Then some synchronization has to be done. After that, Here what we are using is we are inputting some values. Okay. So based on the array index, we are assigning values to the array. We are not giving through scanf. After that, you are allocating the memory space, and we are using CUDA memcopy to copy the matrix A value to device and matrix B value to device, and so on the resultant array. Then after that, that is product. We are allocating space, and next we are calling the kernel dim grid dim block. So in dim grid, the width has to be divided by tile width, and here also width is divided by tile width. Tile width and tile width, comma 1. Already we have assigned value to the tile width. That is used here. That's all. And matrix multiplication dim grid dim block, and resultant array. What about the width? Everything is passed. Uh, and the resultant array is copied back. After that, it is printed. Okay. Then we are calculating time and all. See here. What I have given us something like tile width 2. Yeah. The width is given. I have given the width as 200. 200 and 400. Okay. So this is a huge array. This calculator, and we are getting the result. So very huge. I'll paste this program. In small parts. Otherwise, it won't be pasted everything there. Okay. No indentation is required in C program, so it is not a problem if there is any indentation is missing. Fertile synth is not copied. alien kernel. No, to that it is not copied. Don't bring it. So anyhow, I will upload all the programs later. If you want it now, I have pasted there in chat. Okay, we move to the next one. So this is a complete program without input getting and printing output and all. Okay, so all the kernel code is available here. If you have declared this function here, if it is not working, means you define this kernel as a global function. It's not a problem. Okay, so complete executable code I have is there in the chat. I'll upload later in the sheet. Okay, so next, that's all about matrix multiplication. Next, we'll move to the multi-threading. Okay, so we are having streaming multiprocessor, the SMs, there in the GPUs. Otherwise, we can say that the cores are single instruction multiple threads because the same instruction is executed by more than one threads, and all the cores execute the same instruction simultaneously but with a different data. Okay, so because our GPUs are meant for data parallelism, and at least 32 threads are doing the same thing. Okay, almost same time. Okay, there is no context switching, and each and every thread has its own register. Already we have seen in the programming model of GPU or GPU memory. So there it is represented. Each thread has its own register, and which limits the number of active threads. Okay, that is limited by the register, and threads on each SM. SM will consist of, SM is nothing but the blocks which consists of threads, and warp threads consists of 32 threads in a group. Okay, so and at least 32 threads can execute the same instruction given by to the GPU. Okay, and execution alternates between active wraps, warps, with warps becoming temporarily inactive when waiting for data. If there is no data, means it will wait. Okay, so there is one type of GPU that is called Fermi hardware, and it is having 8 blocks running on the same time on each SM, and each block has 4 threads. Okay, war threads. Okay, So then 8 into 4, we are having 32 hops running on each SM. Okay. And okay, so each clock tick SM warp scheduler decides which warp to execute the next data, and choosing from those, not waiting for data coming from device memory or completion of earlier instruction. Okay, so it won't wait for any memory latency or pipeline delay. Okay, so already some instruction is executed in the pipeline. If it is not finished, but some other thing is coming, means that will be executed automatically. Okay, so sometimes we'll be getting the result in the random way like that. So if there is any memory latency means, so what happens is some other data is read from the GPU, and it will be executed. Okay, so we don't worry about the these all things in detail. Okay, so we'll consider you are having the lot of threads and warps, so you simply write code and execute. And so already we have seen these things a lot. And the spatial locality is, so if we have seen at least 32 threads executing the same instructions. Okay, and the ID is assigned as 0 to 31. Okay, so all are in the same catch line. Okay, then only they will be getting the same thing. So here the catch line is the basic unit of data transfer in GPU, and mostly it will be having 128 byte of catch line. Okay, so 32 floating point operation or 16 double floating. And so each and every access, if it involves different catch line, so latency will be very high, and performance you are getting is very poor. Okay. So next, what's the software view? Okay, and already you know that. Anyhow, once again I'm telling. So first, the GPU card is initialized, allocate memory, and we are doing performing mem copy, CUDA mem copy. Then we are launching the kernel. So CUDA mem copy to return back to CPU. So if needed, the step 2, 3, 5 is repeated. And once everything is done, you have to use CUDA free. And so at the lower level, the higher level, okay, so for GPU, performing all these steps. In GPU, what happens is each instance of the execution kernel executes on an SM. Each and every instance, execution instance, will be executes on a SM, that is streaming multiprocessor. And if the number of instances exceeds the number of SM, okay, so if you are using some 2 or 3 5, 6 or 7 SM, already you will be having 1 or 2 SMs. Okay, and what happens is more than one will run at the at a time on each SM if there are enough registers and shared memory, and the others will wait in a queue and execute later. Okay, that's why I already told. If you want to give, while doing kernel launch, you can give any number of blocks and threads. It won't be a problem. Okay, what the GPU will do is, so it will allocate what are the available SMs are there, that will be allocated. After that, uh, if possible, more than one is executed on the SM based on the availability of threads. Okay. So if it is not available, then everything is waiting on the queue and execute after once it is completed. Okay, that happens in the GPU. All threads within one instance can access local shared memory, but can't see what other instances are doing. Okay, so if two set of instructions are executed means, so that one thread is executing one instruction and another one is executing another is in execution. So using the local shared memory, But these instances won't know what others are doing. Okay, there is no problem in that. And but there are no guarantees on the other order in which the instances are executed. Okay, so we don't specify in what manner the instances or instructions has to be executed in the GPU. So that will be executed based on the availability of SM and availability of threads in the SM. Okay. So in CUDA memory, the host can directly access the global memory and the constant memory in the GPU. Okay. So each thread can do read or write per thread registers, read and write per thread for local memory, read and write thread for shared memory, read and write per grid. See here, read and write per thread for registers. Okay. So thread can read and write registers and thread read and write memory. Block read and write shared memory. Okay. So grid can communicate with the global memory and also the constant memory. Okay, this is a memory hierarchy. Okay. Threads can directly communicate with the registers. Okay. So in the access time is for register, single cycle, shared memory, single cycle. So local memory it is no cache, so slow. Global memory also very slow. Constant memory you can cache, and based depending on the cache locality, the cycles may increase or decrease. So texture memory, DRAM, also depending on the cache locality. And instruction memory that is invisible. It is in DRAM. Okay, it is also cached. So that there are different variable types are available: device local, device shared, device constant. Okay, so you can declare int local where, int share where, int global where, likewise you can declare. So what is the memory, what is the scope, what is the lifetime, everything is given. Okay, so based on the your requirement you can use all those variable. Okay, so if you have used device keyword double underscore device, okay, after that you are having double underscore. So this means this is a global variable in the GPU. Okay, so any variable before that you are having the device keyword, you can say this. Okay, so if it is a global, then it can be read and modified by any kernel. Lifetime of the whole application, also declare array or fixed size, and host code units and CUDA memory. And the device is not needed or optional when we are using local, shared, or constant variable. Okay, so it is optional only. There is no need to use. So there are constant variables are there. It is global variable. The kernel code won't modify these constant variables. Okay, so you can define with the help of this constant keyword. Okay. Okay, you can use CUDA memcopy to symbol all those things for initializing host code. Okay, so the constant memory size is 64 KB, and each SM has a 8 KB cache. Okay, so each and every SM is having 8 KB cache, and so if anything is declared in global memory, so you have to use some pointers to access those um, variable in the global memory. And so you allocated in the host and pass to the kernel, you can use in this way, load star ptr. And so to obtain the address of that particular variable, you can use ampersand of. These are all things Already you are familiar with the C2. And if there is any automatic variable without any qualifier that is reside in a register, and those are reside in local memory. Okay. If I equal to 0 or I equal to minus, so it's simply printing what happens there in the ing. And next is shared memory. So you can use shared keyword. This way you can declare the shared variable. You can declare either int or float. So the main advantage of using shared memory is if you want to communicate between threads, threads wants to communicate in between them. So can use the shared. Already we have used the shared keyword there in the dot product. Okay. So you can reuse the data. So you can use alternate, it is alternative to local arrays in device memory. Okay. Reduce use of registers. Okay. So if you want to use same values or same use when a variable is having same value for all threads, you can go with shared keyword. Okay. So if you want to synchronize all the threads, you use sync threads. Okay, that's all. Okay. So already you have known these all things from the diagram. That is, what is the diagram? The programming model. Okay. Everything is there. So Fermi card, if it is maybe two big blocks means it is having 512 threads. Six smaller blocks means 256 threads. Okay, no shared memory. 512 threads means it is having lot of shared memory. Or four small blocks, it is having 128 threads and each needed a lot of registers. Okay. And global memory is there in the device memory. Okay. So DRAM consists of the global memory. So if you want to store some constant, that also stored in the device memory. Okay, what happens in the device memory is okay. So if you want to store something on the different types of memories, you have to be careful. In constant memory is read only, and read and write shared within a block, shared memory. Read and write within the each thread registers. Registers are very fast, and shared memory is also very fast. And read and write input results. So that is there in the global memory. It is very slow. Okay. So for processing and all, you can use shared memory and the registers. Okay. So both are very fast. Okay, so already we have seen this in dot product. Okay, so here this is the main program. Already I have shared that program. See here. We are synchronizing thread 2. Okay, so all the threads are shared. Okay, the data for all the threads have been shared. So now also we are synchronizing threads in the block. Already we have seen this particular program. And okay, this is a continuation of that program. That's all. Okay, this only happens. Okay, so this is nothing but parallel reduction. Okay, if you want to add all those things. So while considering the dot, I will remember this dot product. Dot product, what we are doing is A naught, B naught, A naught into B naught, and A1 into B1, and A2 into B2, etc. That is multiplied and it is added. See here, the thread 0 is added with thread 4, thread 1 is added with thread 5, thread 2 is added with thread 6, thread 3 is added with 7. Here also the parallelization. At the same time, this and this one is added and this one is added. At last, this and this one is added. We will be getting the result. Okay. So this we can simulate there. Okay. So here in the shared memory, to reuse the global memory data. If I want to reuse the global memory data, you can use shared memory. Okay. So you can use shared memory for storing the or loading the each and every element. And what happens is automatically it reduces the memory bandwidth. Okay. So that means uh, if you use tiled algorithms, the time consumption for the multiplication, matrix multiplication execution is reduced a lot. Okay. So when we are using shared memory, all the threads can access that particular memory. So automatically it reduces the memory bandwidth, also reduces the execution time. Okay, so it is going for tiled width. So each and every thread should have many threads. Thread block, already you know that everything. I simply skip. So we have written these codes in the kernel execution part. Okay, so here it is using shared float for tile width and first matrix and second matrix. So then we are calculating index. Okay, then row index and column index and loop over the MD and ND tiles to compute the PD element, that is product matrix element, that is calculated in this way. So after that, what where it is the threads have been synchronized, then you can do the last step. Okay. So also the uh, for product index, before product index also the threads have been synchronized. So in this way you can use shared and synchronization. Okay. So here uh, one performance of GAT. Okay, while using the shared memory concept, what about the performance? So that is explained here. I have taken it from the internet. I didn't do anything on this programming. So here each and every SM in GAT has 16 KB of shared memory. And so the size is simply the implementation independent, but SM size. But each SM will consist of 16 KB shared memory. Okay, if you are using for a tile width of 16, each thread block uses 2 into 256 into 4 by 22K of shared memory. Okay, it will be using 2K shared memory if for in GAT. And so here up to 8 thread blocks actively executing. Okay, 8 blocks are actively executing. In each block, we can consider 512 threads. 8 into 512, it is having 4096 pending loads. Okay, So 2 per thread, and we'll be having 256 thread per block. Okay. So you are having 8 thread blocks. That means 8 blocks. Each block is having 512 threads. Okay. So these much of load you can able to apply. And if you are having 2 data per thread, so you can use 256 threads per block. Okay, so 2 types of data per block you are giving. So for one block will having 512 threads means one take 256 and another one take 256. Likewise, it is splitted. And if it is tile width is 32, so it will be having shared memory of 8 KB usage per block. Okay. So since it is having 16 KB shared memory, so based on the tiled width, okay, so you can get some shared memory. So if you are using 16 by 16 tiling, okay, access to global memory is reduced in a factor of 16. Okay. So automatically what happens is the bandwidth usage is reduced. So we'll be getting more speed. Okay. So here it is getting 347.6 gigaflops. Okay. So they are representing it's not tiled. It use 10 gigaflops speed. Tile only 10 and 4 cross 4 tiles, 8 cross 8 tiles. Again, the speed increased. 16 cross 16, the tile is the speed is increased a lot. Okay, these are all the references I have seen. So, any doubts in this? Today we have seen something related with uh, parallel execution using both thread and blocks along with tiles. Okay. So if your dimension is high, you can go with some tiles. Okay. So tiles usage, what it will do is it will automatically reduce the memory bandwidth because the usage of high usage of shared memory. Okay. So if more tiles, you will be using more on shared memory. Okay, more space on shared memory instead of using global memory. So if you are using global memory means your data accessing time is automatically increased. So the uh, speed of execution is reduced. Okay, because of more memory access. To reducing that, you can go with shared memory concept. So try to execute the programs already there in the presentation. Okay. So if there is some other way to execute, I will try and tell. Otherwise, from tomorrow onwards, I will execute those programs in our machine and from our college, and I'll show the output. Okay. Okay. Thank you. We'll see you tomorrow.